Alright, so for number 7, if a red cat was to mate with a yellow cat and it produced an orange cat, the allele for coat pattern, because red and yellow mixes to make orange, because you don't see red fur and you don't see yellow fur, but you see just a blend of the two, it is incomplete dominance. Sometimes the colors don't have to mix. The point is that neither red or yellow is being presented, and some new phenotype is being presented. That's why it's called incomplete dominance. Now for number 8, for blood type, both A and B are present, meaning that they are coexisting in this individual, in this heterozygote individual, meaning that it is codominance. The proteins A and B are coexisting, thus they are codominance. In number 9, a true breeding brown mouse with a true breeding gray mouse, and they produce black mice. The thing to note is that doing a test cross with a gray mouse, it's not going to help you, because all that's going to do is it's just going to produce more gray mice. So that does not help. It's not A. Doing a back cross with the black offspring to the brown mouse, well, all that's going to do is it's going to create more black and brown mice. It's not going to produce any gray mice, and that's not going to help you either. Now, if you allow the black mice to interbreed, the black mice in this question represents the F1 generation. Remember F1? The P generation, we have brown and gray. In the F1 generation, we have black. By allowing the F1 generation to interbreed, this results in the F2 generation producing a progeny of all 3 colors. So brown, black, and gray should be present if you were to mate only the black mice together. This is a monohybrid cross, remember? And with the production of an F2 generation, you should see a Mendelian ratio of 1 to 1. This is, of course, following the monohybrid pattern. Thus, this would provide evidence that the allele for coat color would be, let's say, incomplete dominance, because we see black is represented by both brown and gray. So so to confirm how coat color is controlled, you should allow the black mice to interbreed. Alright, so now what we want to look at is in a cross between 2 heterozygote cats, which of these will be a brown female? Considering how capital B is black and that's dominant, little b that's brown and that's recessive. We also know that an X would be a female and an XY would be a male. Now we understand that both of these cats are heterozygote, so we can say BB for both this way, but one of them has to be male, obviously, and one of them has to be female. So with that said, what we could do is we could look at the alleles individually. So only look at B and then only look at the sex chromosomes. We could do that and then by law of probability multiply the 2 probabilities. It's like flipping a coin, getting the chance that it's heads, and then say rolling a die and getting a chance that it's, say, a 3. You'd multiply the 2 probabilities together if you were to flip heads and a 3. Same thing here. We want the chances of getting little b, and getting female. So we're going to look at the B's first. So I'm going to draw my Punnett square, draw out my gametes. Get big B, big B, big B, little b, big B, little b, little b, little b. The chances of that is 1 out of 4. Okay? Now we're going to look at the sex chromosomes. So we have XX, gametes for a female, gametes for a male, XXXX, XY, XY. Chances of that is 2 out of 4. So we multiply the 2 together, 1 out of 4 times 2 out of 4. So we're just going to write it off to the side here. 1 out of 4 times 2 out of 4. And that gets us 2 out of 16, or 1 out of 8. And that's the probability of getting a brown female, crossing 2 heterozygote cats. Now for this question, we're crossing 2 dihybrid heterozygote, double heterozygotes. And assuming 2 genes independently, what is the probability that both are long-haired and white? Well, considering how L is dominant and that represents long-haired, and little b is recessive, which refers to white, we need anything that's big L, little b, or big L, little b. We need either one of these two genotypes. So what we could do is, like in the previous question, just look at the alleles independently and then multiply the two probabilities together. So let's try that. Little big L, little L, big L, little L, LL, 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 LL. These 3 would get us long hair, so that's 3 out of 4. Then we cross the other trait, big B, big B, big B, little b, big B, little b, little b, little b. We're looking for this one, that's 1 out of 4. So we're going to multiply the two together, 3 out of 4 times 1 out of 4, and that equals 3 out of 16 chance. You could also do, just a typical way of doing a huge 4x4 Punnett square by, taking these gametes and getting all the possibilities. So big L, big B, big L, little L, big B, little L, little b, and then put them up all on top. That's fine too, but the thing is, I find that this way is faster, because especially for this next question where you have 4 alleles to look at, doing that huge Punnett square is just really time consuming, and you don't have the time to do something like that. So for this question, we're going to do what we did for the previous question and look at all the alleles individually to get this. So we're looking for big A, big B, little c, big D, and we're crossing, like looking at the A's, we're crossing an AA parent, big A parent, with a big A parent. Just cross, filling them in. 2 out of 4 chance. Now we're crossing, looking back at the parent, big B, little b, big B, little b, and we're looking for this, so 2 out of 4 chance. Then we're going to look at the C, big C, little c, big C, little c, cross them, big C, little c, big C, little c, little c. We're looking for little c, so 1 out of 4 chance. Then we're going to look at the D's. We have big D, little d, cross with big D, little d. Big D, big D, big D, little d, big D, little d, little d, little d. And we're looking for big D, so right here, 1 out of 4. Then we're going to take each of these numbers, 2 out of 4, 2 out of 4, 1 out of 4, 1 out of 4, and we're going to multiply them all together. Sorry, my camera cut out, but we're just going to multiply them together. 2 out of 4 times 2 out of 4 times 1 out of 4 times 1 out of 4. You could reduce these if you wanted to, make it easier for you. 1 out of 2, 1 out of 2. Half times half equals 1/4 times 1 over 4. That's 1 over 16. 1 over 16 times 1 over 4. That equals 1 over 64. And that's your chance. Sorry, that's your probability. Alright, so for the last question in regards hemophilia and how it's an X-linked chromosome, let's say we nominate big H as being normal, and that's a dominant allele, and little h is recessive, and that applies to hemophilia. Well, if the father is normal, we know for sure that he must not carry the allele for hemophilia. So he must be normal. And we know that his Y chromosome, doesn't carry any information, any regards to the trait. If the mother is normal, and we know that her offspring will be hemophiliac, then we know for sure that she is a carrier. So we can write this. Big H, little h. And we can proceed by drawing a Punnett square to see if any hemophiliac children could arise. And if they do arise, under what conditions. So I'm just filling out the Punnett square as we would, as usual. Now, if we were to look at this top row, we have a normal, non-carrier female and a normal carrier female, meaning that no hemophiliac females could arise from this cross. If we were to look at the males, we have one normal male, but one hemophiliac male. So for two normal parents to mate and to produce an offspring that does has hemophilia, the offspring at first has to be a male and the mother has to be a carrier. That's pretty much what I wanted you to demonstrate for this problem. To show me that if two normal parents were to mate, the only circumstance that a hemophiliac offspring could arise is if it was a male. And yeah, that's pretty much it. Any questions? Jesse?
Yeah, Mr. Choi. Yes, science!